At 99% of the speed of light, the universe in front of you turns blue, and the universe behind you turns red. And the faster you go, the more the entire sky compresses into a single blinding point directly ahead. That is not a visual effect. That is geometry and physics doing something real to the light reaching your eyes, and it gets stranger from there. Start with the Doppler effect, which you already know from sound. An ambulance approaching you has a higher-pitched siren because sound waves are compressed in the direction of travel. As it passes and moves away, the waves stretch out and the pitch drops. The same principle applies to light. A light source moving toward you emits waves that are compressed, shifted toward the blue end of the spectrum. A source moving away emits waves shifted toward the red end. This relativistic Doppler effect scales with velocity, and at a significant fraction of the speed of light, it becomes dramatic. At 10% of the speed of light, the shift is noticeable but modest. At 50%, stars ahead of you are noticeably bluer and hotter looking. The wavelengths compressing into blue and ultraviolet range mean stars that would normally appear yellow-white now look blue-white. Stars behind you redshift toward orange and red, some dropping into the infrared and becoming invisible to the naked eye. At 90% of the speed of light, the effect becomes extreme. Stars that were previously in the visible spectrum ahead of you are now shifted into ultraviolet and even X-ray wavelengths, invisible to human eyes but carrying far more energy. Simultaneously, a phenomenon called relativistic aberration takes hold. This is not Doppler. It is a separate geometric consequence of moving fast enough that the entire forward hemisphere of the universe appears to concentrate into a smaller and smaller cone ahead of you. Stars that should be at the sides of your view are pulled forward. The sky behind you empties. The sky ahead crowds with increasingly energetic light. At 99% of the speed of light, you are receiving radiation that has been blue shifted so dramatically that it would be lethal. X-rays and gamma rays are now arriving from what were previously harmless visible light stars. The concentrated energy in the forward direction is not just bright, it is physically dangerous. Simultaneously, the universe behind you has essentially gone dark in the visible range. Most of it shifted into far infrared and radio wavelengths. None of this is hypothetical decoration. The mathematics comes directly from special relativity, and the individual effects have been measured. Particle accelerators routinely accelerate protons to 99.9999991% of the speed of light in the Large Hadron Collider. At those speeds, the relativistic mass increase, resistance to further acceleration, is enormous. The protons behave as if their effective mass has increased by a factor of over 7,000. This is why no particle with mass can reach the speed of light. The energy required to accelerate it approaches infinity asymptotically. Time dilation is where the personal consequences become genuinely staggering. At 99% of the speed of light, the Lorentz factor, the multiplier that describes how stretched time and compressed space are, is approximately 7. 1 year for the traveler corresponds to 7 years for a stationary observer. At 99.99% of light speed, the Lorentz factor is approximately 70. 1 traveler year equals 70 observer years. The twin paradox illustrates this. If one twin boards a spacecraft, travels at a significant fraction of light speed to a nearby star, and returns, they come back younger than their sibling who stayed on Earth. This is not symmetric. The traveling twin experienced genuine acceleration and deceleration, which breaks the symmetry. The effect is real, and has been measured with atomic clocks on aircraft, which tick slightly slower than identical clocks on the ground, precisely matching the predictions of special relativity. At the most extreme velocities, a journey across the galaxy, roughly 100,000 light-years, could, in principle, be completed in a human lifetime for the traveler, while 100,000 years pass on Earth. The traveler arrives. Everyone they knew died thousands of generations ago. The universe does not break these rules for anything with mass, but it is generous with the consequences for those who approach the limit. Follow for more physics that changes how you think about space and time, and tell me, if relativistic travel means you could cross the galaxy in a lifetime while thousands of years pass on Earth, would you go, knowing you could never meaningfully return?